This is your pre-lab video for the Colligative Properties lab. Colligative properties are those properties of solvents that can change when solute is dissolved in them. And the modification of temperatures of phase changes like freezing point, melting point, and boiling point are examples of a changing colligative property of a solution. And the magnitude of the colligative properties, or the magnitude of the temperature change, depends only on the dissolved particles and the amount of dissolved particles that are within the solution, not on the type of solute that's dissolved. Boiling points are elevated when solutes are dissolved in solution, and freezing points are depressed or go down. In part 1 of this lab, you'll be investigating saturated solutions and solubility. The term solubility is used to describe how much of a particular salt dissolves in that solvent. And it depends on the type of salt that it is, the solvent that's being used, as well as temperature. When a solution contains the maximum number of solute particles, it's said to be saturated. And you can identify a saturated solution by once you've tried to dissolve as much as you can, you've stirred, you've waited long enough, and there's still a little bit of solute left in the bottom of the flask, then the solution above it is saturated. It's holding as much as it can. You'll be making saturated solutions of 2 different salts, and you'll have to calculate the concentration in grams per milliliter. This is also a density, so density is a type of concentration. So you'll be using the solution mass as well as the volume of a pipette that you'll be using. And once you get your information and generate your data, you will be answering the questions, do all solutes have the same solubility, and do all saturated solutions have the same density? As you go through the lab, make sure you record some sources of error as you see them so that you can put them in your report. In part 2, you'll be experimentally determining the boiling point elevation constant for water. And this is the amount of boiling point change for that solvent. So the KB is different for every solvent. And remember, boiling point's going up when we dissolve solute in it. This is the apparatus that you're going to be using. So we're going to increase the temperature of our water using a hot plate. And this is a temperature probe here. So we'll be using a temperature probe that will be collecting our data, our temperature data, and we'll be using a hot plate. In order to determine how the boiling point has changed, we need to know what the boiling point is for pure water. So you'll be heating your water, and once it starts to boil, you'll record the temperature at least at 4 different points. And you want to make sure that you're recording the maximum temperature. Because remember, during a phase change, the temperature doesn't change. Even as you add more and more heat, the energy is going to change the phase from the liquid to the gas and not changing the temperature. So once you reach that maximum boiling point temperature, that's the boiling point of your pure water. You'll repeat this with the salt solutions, the dilute salt solutions that you make within the lab. And this time, you're going to be recording the temperature as you heat it. So here we have temperature versus time. So as you're adding heat and the time is going on, the temperature of the liquid solution is increasing. So this is governed by the Q equals MC delta T. Once you reach the boiling point, the temperature will be maintained. So you will hit a flat spot on this graph. Once this temperature starts to level out, that's your boiling point. Continue to record the temperature throughout this, but once you start to see the temperature going up again, this is erroneous here because your solution is starting to evaporate and the concentration is changing. So we don't want any information out here. We want where it's level, so this constant temperature. Your calculation for KB is your change in boiling point, so this is from the difference between pure water and the solution, equals the Van't Hoff factor, which is the number of particles that your solute breaks up into when it dissolves. So for sodium chloride it would be 2, because we have 2 ions that this dissociates into, times your constant, which is what you're solving for, times molality. And you have to calculate molality, and that's moles of your solute per kilograms of water. And when you do this calculation, you want to assume the density of water is 1. So 1 milliliter per 1 gram of water. Change in temperature, and you'll solve for your KB. Anytime you do more than one trial for any test, you don't average your data and do the calculation. You want to calculate, and in this case, calculate for KB for each of your trials, take a look at the results, and average. So percent difference, you want to determine what's the difference between your experimental data, the average KB that you generated, compared to the accepted value for water, which I'm giving you here is 0.512. And it's the accepted value, that's the 0.512, minus what you get. This is your average of your trials divided by the accepted value times 100. Safety for this lab, all the solutions may go down the drain. However, you will be using boiling chips that you do not want to throw in the sink. You don't want to just dump them in the sink. You need to throw those in the garbage. Be careful with the hot plate. The hot plate surface does look the same cool as it does hot. And this is the most important thing. Please do not melt the temperature probe wire. This has happened before. Make sure you keep that temperature probe far away from the hot plate surface. And this concludes your pre-lab video.